are you ready?
Yeah.
Turn on yet? Oh, you did? You started?
Yeah.
Okay. The warning would have been nice. All right. We are taping. Today we're going to do something which I used to do every year, but then I decided, what's wrong? Yeah, man. So because in the interest of time, no, just keep the camera there, fine. In the interest of time, I'm probably not going to do this with my other classes, but I'm going to do it with you because for whatever reason we got a little bit ahead, and then because of the Friday thing. Okay, so period 4 and 8 will be watching, and they will learn. So
Hey, everybody.
I didn't really say anything important yet, don't worry. I sort of told you that the unit was over, but I was joking. I want to talk about today, I want to talk about the determinant some more. And what I want to do is, I want to talk about some properties of the determinant. And for the purposes of this class, for the purposes of today, let's define the determinant to be, or let's think of it as the area of the parallelogram determined by the column vectors. So if I want to compute this determinant, I draw the column vectors. So there's AC, there is BD, and then I want to know the area of that rectangle parallelogram. So we have previously determined that its area is
AD minus BC.
AD minus BC. And so the simple determinant is just AD minus BC. Okay, cool. Alright, well, let's explore, especially now that we understand some of these different transformations. Let's explore what happens if, for some kind of reason, I just decide to multiply the one of the columns of the determinant by a constant. Okay, it's a constant. So if I multiply column 1 by a constant, k, how does that affect the determinant, first of all, and second of all, why? Okay, well, we have basically two options. What's one thing we could do? What do you mean by factor it out, exactly? Just take it out of the determinant entirely?
Yeah, and then multiply it by something.
Wait, hold on, Fausto's doing some rambling. Wait, what's probably the simplest thing to do? Just like do it, yeah, okay, so if you, so the lame way would be to trust this previous formula, and so what do you end up with?
KAD minus KBC.
Yeah, you get like KAD minus KBC. Yeah, with a bigger sentence. So it's just K times. Okay, so it appears that when I multiply a column by K, that increases the value of the determinant by factor K. Rourke, you with me? Alright, but this is like kind of boring. I want to like understand what it actually means. So, what does it all mean, man? What should we do? Murad?
You're increasing one of the vectors by factor K.
Yeah, Murad says draw a picture. Everyone draw a picture. If I define the determinant to be the area of the parallelogram determined by the column vectors, then I should probably draw the column vectors, right? Getting the hang of this? So here was like my original AC. This was BB. But now, what have I done to that first column? Yeah, I multiplied by k. So then we should extend this vector by factor k, like, I don't know, suppose k is like, I don't know, like 2 or 1.5 or something. So we get this new vector. Rob, this is like what you were talking about, right?
Yeah.
Yeah, he's just like, yo, stretch out that vector by factor k. Now this would be, terrible marker is what this is. Now this vector would be KA, KC. right? KAKC. Okay, and what's the area of that parallelogram? Yeah, if we now do this, I have this purple thing, and does everybody agree that this purple thing is like, so then this was my original one in green. The purple one is K times as much, right? Why? Can you articulate exactly, how do I know that's K times as much? Geometrically, like what have I done? June, what have I done?
You're asking.
Yeah, what I do, like why is that K times as much? Just explain.
Because you extended one vector by k.
Okay, I mean look, I agree, but give me a little bit better explanation. I extended one vector by K,
One
so.
base is multiplied by 2, so there you
Yeah, okay, that's probably pretty good, right? The height, if you think of it, the area of a parallelogram was just base times height. So if that's the height hasn't changed, right? All the change is the length of one base was whatever that was, and now it's K times as much, so the area of the parallelogram shouldn't change. Cool. Anything else to say? I feel like that's good. Okay, good. So, okay, here's one that I actually just don't understand. I've also put in, I don't know, 5 hours over a period of years trying to understand this, I still don't get it. So, the transpose of any matrix, so here we go, ready? Let's take A, B, C, D. And we know that the determinant is AD minus BC. We'll take the transpose of this matrix. What do you get? So that's like A, C, B, D, now like that. All right, what is that determinant? Same. All right, yeah, the value of the determinant does not change when you take the transpose. It makes sense in certain contexts. It actually makes no sense, in my opinion, geometrically. But if you think about the recursive definition of the determinant, then it actually kind of does make sense. Because you're sort of just switching like all the spots and kind of flipping the signs. Anyway, so all right, so it's probably not a surprise that, for example, what happens if I multiply a row by factor k?
Probably the same thing.
Yeah, probably like. Wait, what do you mean by same thing?
Like the other one.
Okay, good. Do it out with algebra, and then also draw a picture that represents the situation. It's kind of hard to draw, actually.
Nothing under entire paper.
Those are like the original vectors, and that's my original parallelogram. Now I'm supposed to graph KAC comma KBD. Did you guys do that? It's kind of weird, right? Like if K is like 2 or something, then it's now I kind of go like here. What you guys got? KAC. Then it's kind of like. And then KB, comma D would be like the same height, but now like B would be like here or something, right? You guys getting this kind of like sort of at first glance, like what am I doing? What's going on? That's KB, comma D. So what's up with this parallelogram? That's a pretty decent picture. Tony, what's up?
Well, all of the y's are the same,
Uh-huh.
but the x's changed.
Yeah. How'd they change?
By factor k.
Yeah, I guess, right? Well, we changed all the x's by factor k. So like, actually, how would you describe geometrically this, what we did to this parallelogram? Everest.
So it's kind of like you took the top corner point, you just like dragged it over to like a new point, and like all the points followed.
Yeah, okay. Yeah, we drag everything this way. So it's kind of just like it's like a one-dimensional dilation, right? In some ways what we did is we just dilated by factor k in the x direction. So if we dilate this parallelogram by factor k in the x direction, well then it kind of makes sense that the area increases by factor k. Does this make sense? Okay, over here what I did was I dilated it by factor k along the vector AC, which made for kind of a prettier picture. Whereas here I dilated by factor k along the vector AC, here I dilated by factor k along the x-axis, but still should increase by factor k. Okay, cool. So these are the kind of pictures you need to draw to understand. There's also this weird thing. Just, by the way, what are we maybe kind of getting at? It's like the thing we did on the very first day of this class. You can multiply a row by a constant. What's the other thing you can do? Mike said something, no? What are the three row operations? Yeah.
You can switch rows.
You can switch rows. Yeah. So what does that do? What happens if I take the matrix A B C D and I just like swap like rows or whatever, and so then suddenly I get like C D A B. How does that affect the determinant? How does it affect the determinant? This becomes C D A B. What's this?
Yes.
Did I do something wrong? They're just telling me the answer. This is BC minus AD. Yeah, so conclusion? It's like the opposite. Yeah. Oh, by the way, this might be a good time to discuss what the hell is a negative determinant? After all, since I told you it was the area of the parallelogram is determined by the column vectors, no one's gotten on my case about that yet. Usually, like, people are screaming at me, like, yo, Mr. Rose, you liar. You told me that the determinant is the area formed by the the dark area. Yeah, that's actually a pretty good answer. Yeah, so what does it mean if the determinant is negative? It tells you that the vectors cross in the transformation. So watch. Suppose I have my original unit vector 1, 0, and then I have my vector 0, 1. Let's just suppose, for fun, that 1, 0 gets sent to like, I don't know, like 1, 2 or something. So this went there, but 0, 1 got sent to like 3, 1. Then there was like a cross, which creates like negative area or something kind of weird like that. If you think about it, do you guys kind of understand this weird arrow picture?
Yeah.
What is the transformation in which 1, 0 goes to 1, 2 and 0, 1 goes to 3, 1? Well, it would be this matrix, right? It would be 1, 2, 3, 1. And what's the determinant of that matrix? It's like negative 5. Cool. Okay, so anyway, all right, last thing, basically last thing. Oh no, almost last thing. What's the other thing we know how to do? So we can multiply a row by k. We know how that affects the determinant. It multiplies it by a factor of k. Switching rows multiplies it by -1 for mysterious reasons I don't fully understand. What's the other thing you can do?
You can replace a row with the sum of multiples of the rows.
Yeah, it's actually prettier if you do it with columns though, so let's do columns. So suppose this was my original matrix, A, B, C, D. And what I'm going to do is I'm going to replace column 1 with the sum of column 1 and column 2. So make this A plus B, C plus D, and make this BD. Okay, compute the determinant and then draw me a picture that explains the whole situation. Yeah, apparently this move doesn't change it all the time.
No, that's not interesting.
So A plus B times D minus D. So surprise, it's still AD minus BC. Did you draw a picture yet?
No.
Okay. So you got so shy. I turned the camera on, everyone got shy. It's kind of awesome. So here was the original. Again, I'll draw the original guy. So that's AC and BD. Better colors. So I can draw. This was the original parallelogram, right? Do that, color that like in green or whatever. But now suddenly I am not, so on the same axes I'm going to draw the parallelogram determined by those vectors. Well, what is the vector A plus B comma C plus D?
It's like way out.
Way out, how far out?
A plus
Like
B.
the tip of that parallel.
How about like that corner, right? Because like vectors.
Yes.
Yeah. Yeah. Yeah, that is in fact A plus B comma C plus D, right? Because it's just a vector sum. You guys with me?
Yeah.
Yeah. So the new parallelogram is the one formed by those two vectors, and if you kind of like draw that, you get like a this. That was the picture I was hoping you guys would just spontaneously produce. Talk to me about that purple parallelogram versus that green parallelogram. One word, shear. It is definitely a shear. Yeah, we're just shearing that guy, so of course the purple guy and the green guy have the same area. So you guys see what I'm kind of doing? I'm sort of like proving determinant properties via like geometric transformations. Okay, here comes the hardest one. Yup. Here comes the hardest one. Instead of replacing a column with the sum of it and another column, let's replace a column with the sum of it and a multiple of another column. Okay, so what happens if I replace column 1 with column 1 plus m times column 2? First do it out and see what you get. And then draw a picture. The picture's really cool. Yeah, so first off I have my like original parallelogram. Now somehow I need to create the vector a plus bm and the vector c plus dm. Well, I guess the best way to draw the vector sum is to like draw the parallelogram and then just draw the diagonal, right? So somehow I need to make the vector MBMD. So step one, extend out BD by amount M. So then that becomes you guys with me? And then what's up?
You add that to AC.
Yeah, then you add that to AC, and the simplest way to add that to AC is to just like do like that, right? Yeah, exactly. The vector, it's just another shear. Yep. Now we go, and by the fact that that corner of that parallelogram is the vector sum of AC and BM plus DM. So this is A plus BM comma C plus DM. And therefore, what is the parallelogram determined by these two vectors? It's like that one. You guys see what's going on here? Picture's getting kind of complicated. Alright, cool. Alright, so it turns out I proved all these various properties of the determinants. If you take the determinant as defined as the area of the parallelogram determined by the column vectors, then I get that if you multiply a column by k, the determinant increases by a factor k. The transpose is always the same, so it shouldn't surprise you that if you take k times a row, the determinant's going to increase by a factor k. If you replace a column with the sum of it in another column, it doesn't change at all. And even if you replace a column by the sum of it in a multiple of another column, it doesn't change at all, right? The last thing I forgot to say is that the purple and the green have the same area because they're just shears. Okay, armed with this, nice. Armed with this, we can prove Cramer's rule. Did I talk about Cramer's rule in this class at all? For like 5 seconds one day or not?
Yeah, you did.
Not even 5 seconds? I thought I did.
You did.
Cramer's rule came from this one time when we solved the system of equations. I think that's when the time I usually bring it up. If possible, if you could like move it, like maybe, I don't know, do something. You can move it, like you could pick it up and just move it back over, potentially. Or you can just leave it there. Okay, so what is Cramer's rule? So we're going to do this 2 ways. We're going to do it the geometric way, and we're going to do it the algebraic way based on these properties that we already learned. Okay, so what does Cramer's rule say? Does anyone remember? It's in your notes. I thought we did this maybe. Yeah, right? It says, Cramer's rule says, if you have a system of equations, ax plus by and cx plus dy equals e equals f, then we did a whole bunch of stuff, and we solved this system, and we found that x was some stuff, and we said, oh, that actually can be expressed as the ratio of 2 determinants. Remember this?
Oh.
Yeah, it's really good. It's so useful.
It was like,
Really?
Yeah.
I don't know if he's being sarcastic or not. So both of the solutions to this system have have denominator AD minus BC, and then remember the numerator of the x was what you get when you replace E and F in for the x column. So we got EF here. Whereas the numerator of the y could also be expressed as a determinant. It's the what happens when you replace the second column with EF, the sort of y column. Cool? Yeah. Okay. So besides just the fact that we brute forced it out and got that, I don't have any understanding for why this should be true. Okay. So here comes the proof, and the proof is geometric. It's actually very much like that picture we just did, to the point where like it's almost redundant, but it's still kind of cool. All right, and here's what we do. What we're going to do is we are going to think about this system of equations as no longer being a system of equations, but in fact as a statement about vectors. What this equation really says in disguise is that if you multiply x times column vector AC plus y times column vector BD, then you just get column vector EF. Good. Okay, so let's do it. So this is our sort of reinterpretation. So we reinterpret this system of equations as meaning that. Okay, well, if that's my interpretation, then somehow I need to prove. So I'm just going to prove the x case, and then the y case is just like the same, right? So the x case, what this x case really says, if you think about it, so somehow what I need to show is that if I have this determinant, A, B, C, D, and I multiply it by x, that what I get is a new determinant, E, F, B, D. All right, well so if I can prove this, then I'm done, right? Then I just divide both sides by the thing, right? Okay, so this is my goal, show this. Well, now that we're so smart, we realize, okay, this is really saying something about like areas of parallelograms, right? This says if you take this parallelogram and scale it by factor x or something, then you'll just get this parallelogram. All right, so we just do it. Let's make the picture. So I might have like run out of space to make this picture. Oh, well, I'll try it. So vector AC. And here is vector BD. And here is my original parallelogram. Okay, so here is my new goal. My new goal is to somehow understand that this is to work the givens into my picture somehow. Well, what are the givens? The given is that if you scale vector AC by x, and you scale vector BD by y, then you get vector EF. Right? Okay, let's draw it. Let's scale vector AC by x. Good job. And this is like XA comma XC. Okay, now what?
Scale BD.
Now let's scale vector BD by quantity y. So that's by comma dy. Okay, cool. All right, and now if the sum of AX, if the sum of this vector and this vector is EF, then draw EF. What is EF? It's like the diagonal, yeah. You guys are learning something over there. Right? So this must be EF. Right? And basically, what I've really done is I've like taken this, so let's see, how am I going to draw this? I've taken this original parallelogram, I have scaled it by factor x. So if I scale it by factor x, I get this like new parallelogram. And do you guys see how this red thing is x times as big as the black thing, right? Okay, and then what is the meaning of this determinant, EF, what's the meaning of this determinant right here? Do it with your hands. Brad? Yeah, it's sheared up, right? It's the rectangle determined whose columns are EF and BD. So the rectangle whose columns are E, F, and BD is this one. So this is like the kind of proof of Cramer's rule purely by picture. That purple rectangle has the same area as the the purple parallelogram has the same area as the red parallelogram because it's just a shear. And the red parallelogram has x times the area of that original tiny little black parallelogram. So in fact, I have proved that if you start with the original parallelogram, which represents the area of this determinant, and you scale it by factor x, the left side of this equation is basically the red parallelogram, then you get, on the right-hand side, the purple parallelogram. Cool? And you just divide. All right, what's left? Cramer's rule. That was the 2 by 2 case. Now all we have to do is the 3 by 3 case. Get ready to draw a couple hundred parallelepipeds. Just kidding. If we assume that all of these properties of determinants also hold for 3 by 3s, then we can prove the 3 by 3 case doing a little bit more algebra moves. So you might actually like this better. So watch. What is the 3 by 3 case of Cramer's rule? You may have like Googled it or something because I put it on a homework assignment.
That's right. It's like the same thing.
Okay, what do I have here? Of course, the generic system of 3 equations and 3 variable system of equations. And what does Cramer's rule say in this case? Well, it also says that x is the ratio of 2 determinants. The denominator